One of the most asked questions among math scholars and mathematics in general is what exactly is the constant e? In order to figure this out, we are going to need to look at how the number e came to be and for what purpose it serves. The number e is an irrational number. Now, if you don't know what an irrational number is, it is a number that cannot be written as a ratio or a simple fraction. Just like pi, the number e is a numerical constant. Now, we know that pi is the ratio of a circle's circumference to its diameter, but where does e come from? The number e comes from the concept of natural growth. Natural growth can be observed in things that occurs in nature exponentially, such as population growth. But one of the best examples of e and how it was first discovered is compound interest. Unlike simple interest, compound interest is where interest accumulates on the principal and prior interest. The general equation for interest is interest equals principal rate time. Now, interest can be compounded multiple times within a given year or interest rate period. Each year, for multiple compounding intervals within each rate period, the formula for compound interest becomes A, the amount equals the principal parentheses 1 plus rate over the number of compound periods in 1 year to the power of time in years. N is the number of times the interest is compounded in a given year and is therefore the total number of times it is compounded. The amount gets closer to Euler's constant as n increases. If we put $1 into a bank account with 100% interest rate compounded annually, you will get $2 at the end of the year. If it's compounded semi-annually, you will end up with $2.25 quarterly, and you will end up with $2.44 monthly, $2.61. This can be proven using this table. As you can see, the more that a dollar is compounded by 100%, the closer to e we can get. Although the number gets super close to e, it will never actually reach it. Using this mindset, mathematician Jacob Bernoulli would go and define a limit that would show how the equation would eventually equal e as n increases towards infinity. This equation with limits is, as n approaches infinity, 1 plus 1 divided by n to the power of n equals e. Infinitely compounding interest reflects an exponential growth which directly relates to e. That said, e was first discovered with algebra in the 17th century. E was almost discovered when logarithms were invented in 1618 by John Napier. Credit is given to John Napier for first thinking about e and being on the right track towards it. Logarithms immensely aided longhand computation by allowing multiplication and division to be carried out by addition and subtraction. Euler's constant is thought of as a base that represents growth continuously in proportion to the current quantity. E and the natural logarithm is used more than other bases because they are directly interpretable in proportional differences. The value of e is about 2.718 and was calculated to 869,894,101 decimal places. An efficient way to calculate the value of e is to use the infinite sum of factorials. Factorials are simply just the products of numbers indicated by an exclamation mark. Euler was able to prove e could be found with this setup. Because the solution of these natural logarithms comes out naturally either as f of x or log of x, the slope of the number e on a graph is always proportional to the y value on the line at any point, which allows it to be used for many scientific and mathematical applications. Examples of this are compound interest, Bernoulli trials, derangements, optimal planning problems, asymptotics, and standard normal distribution. It also has many applications in calculus. D over dx e to x equals e to x. This can be proven. Since y equals e to x is the inverse of y equals natural log x, we can obtain its derivative. Therefore, on taking the derivative of both sides with respect to x and applying the chain rule to natural log y, 1 over y prime equals 1 and y prime equals y, which is d over dx e to x equals e to x. In calculus, the function e to x is its own derivative and integral. This tells us at all points along the curve f of x equals e to x, the slope is equal to e to x, the area under the curve is equal to e to x, and the y value is equal to e to x also.